Okay, welcome to the course Digital Communication. So today I'm starting the subject. I'm sorry that I'm a little late. So I thought of giving the first lecture on Wednesday, but I needed some time to actually prepare for the way I wanted to teach this semester. It's not about the material, but about the trajectory by which I will approach. So right now I am kind of convinced about what trajectory I will use. The prerequisite I have already discussed, that you need to understand signals properly. So introduction to digital communication. So right now I will formally introduce digital communication, and I will plan the overall semester material. So the immediate prerequisite for this course is analog communication, which you have done in the last semester. So what you have learned, that there is some signal source, and the source is generating some continuous time waveform. Suppose this is xt, so this is a continuous time signal. This can be a complex valued signal. So xt is like a function from real line to the complex plane. So it can be a in general complex valued signal. So you know that the like in phase and quadrature phase, so how the analytic function is generated, that is a complex valued signal. And then there is some channel. Now this channel is a physical like thing, which can be a copper wire, twisted wire, or it can be like optical fiber, it can be like wireless media, that is the free space, it can be optical fiber, it can be even for acoustic waveforms, optical fiber, it can be ocean, so the water, that can be a channel. So when that signal you want to transmit through that channel, and there will be some receiver here where you will receive the channel. So you have seen there will be some signal YT which is received here. So you have in analog communication, you have used this kind of block diagram, signal flow diagram, where since this xt, its spectrum and the channel's spectrum, the band, may be mismatched. So you need modulation and stuff, and again after receiving the signal you need demodulation such that to get it back to the original spectrum. Now what kind of sources are normally used? So we use in analog communication, for example, we use it for speech signal, it can be for audio signal, it can be for video signal as well, say TV signal, etc. So those signals are essentially band limited signals. So band limited signal means their spectrum, if you compute that their spectrum is in a particular band. So if they are real valued signal, the spectrum will be symmetric, otherwise it can be asymmetric also. But we understand that suppose you take the real valued signal, for example speech signal, so typical frequency range is say 100 Hz to say 3.4 kilohertz. So the signal will be here, and it will be say symmetric in the other side also. So minus 100 Hz to minus 3.4 kilohertz. Audio signal, it is like say 20 Hz to 20 kilohertz, like that. TV signal can be even more. So this kind of spectrum, which is the source spectrum, that is sent through some channel, which are some real channel, and they are having some kind of linear or non-linear behavior. So some kind of filter, and they will have a particular kind of amplitude and phase representation. So they will transform the input amplitude and phase in a particular way. So the receiver design in analog communication is basically to remove the artifacts like caused by the channel, and also to demodulate, because you are transmitting this signal which is between 100 and 3.4 kilohertz, and suppose the channel is say a few megahertz or even gigahertz. So you have to translate it in the spectrum domain, so which is called the modulation, and then you have to demodulate it at the receiver to get it back the original signal. So when you basically call in a telephone, what you do, your signal will be modulated and sent through the channel, then at the receiver end it will be again demodulated, and the other person will receive the voice, will listen to the voice. So this is the analog communication thing. But one thing which is assumed when analog communication is taught is that the spectrum is definitely limited, it is band limited, but what about the time? So time is assumed normally to be the entire real line. So time is between minus infinity and infinity. So the signal is like persistent signal, it is all like present for all the time. But is that a realistic assumption? The answer is no. It is not realistic assumption. All signals are essentially transient signals. They are having like which are having some importance, this speech or DOTV, etc. So when I am speaking to you and I am recording my voice, so this voice I am recording for say 55 minutes. So that 55 minutes, so I am starting at time t is equal to 0 and it is running up to say 55 minutes. So this is a finite duration. It's not minus infinity to infinity. Similarly, all signals are essentially finite duration signal. So they are finite duration signal. And if so, then if you are having a channel and that channel you are specifying some band of the channel for transmitting this particular signal which is emitting from a particular source, and you are using the entire time, the minus infinity to infinity, the entire real line of time of that particular band. That band can be a particular specific band for this source, but we know that the source is having finite duration, the time is finite. Then the channel, except that time window, for all other time the channel is unused. So you are basically wasting your resource. So what in analog communication, what people thought that okay, what we can do, we can reallocate that particular channel to other sources, to other say radio stations or to other subscribers of telephone. So instead of like single source, there can be multiple sources, say source 1, source 2, etc. And we can like use those sources. Suppose there are some 100 of sources, and we can use those sources at different time to use the same band of the channel. So this idea of using the same timeline for different sources is called time division multiplexing. This also you have seen, right? TDM. This was a common practice in analog communication, but in digital, when we are moving towards digital communication, this thing is more prominent. But for that we have to first understand a particular behavior of a simultaneously band limited and time limited signal. We want to show that those signals are fundamentally digital. Then it will motivate us in a better way to go for digital communication. So I will do that in an elaborate way, of course. But I can just mention that what surprising result we will obtain. So the surprising result, first surprising result we will obtain is that for band limited and time limited signal, simultaneously band limited and time limited signal. Now here I should put a note of caution, because we will again show that from uncertainty principle, Eisenberg's uncertainty principle, we know that a signal cannot be simultaneously band limited and time limited. That again we will prove. But when I am saying that these practical signals which I just discussed, they are essentially band limited and time limited, that means they are approximately band limited and time limited. So if you make them forcefully time limited, then they will not be truly band limited. But again, if you make it forcefully band limited, they will not be truly time limited. However, approximately they will be band limited and time limited, and there will be some energy which will be dissipated outside the band or outside the time window. That loss we have to encounter. Now for this kind of band limited and time limited signal, and say let us talk about some finite energy signal of course the energy cannot be infinite, and the signal is sent through a channel which is having some finite noise. So the noise is not infinite, or finite resolution we can say, noise or resolution. Then we will prove the famous Fox theorem, which is saying that for such a case the signal dimension, you know about signal space, you have heard the 8 lectures of Fourier series and transform, right? So the signal space dimension becomes finite, and that dimension is approximately 2wt, where w is the bandwidth and t is the time width. Not only that, the number of possible signals, so bandwidth is having bandwidth w and time width is t, and suppose finite energy, say let us say the energy is E and the resolution is say epsilon. Okay, then like satisfying all these 4 criteria, the number of such possible signals is also finite, and we will prove that that number will be wt log, actually not wt log but E by epsilon whole to the power wt. So which in binary representation we can use using wt log E by epsilon bits. So since this is finite, the number of such possible signals which the source can generate is finite. There is a like strong rationale behind thinking that then why do we need to represent them using analog signal waveform, using continuous time? Because when you are doing in continuous time, the dimension is becoming uncountably infinite, and there are, like, we are always thinking that there is uncountably infinite number of such signals available, but in reality that is not true. There can be at most some finite number of signals with these 4 requirements, which are essentially the signals which you want to send through the channel. So this is the strongest rationale behind digital representation of a signal. So we'll learn that. Then we will go to the like digital representation. So we'll talk about sampling theorem, and then to like have the ranges finite, we need quantization, and this quantization we will use this resolution or noise information to do the quantization, such that the quantization error goes below the resolution of the signal. So in the block diagram, so when the signal source, the original signal source is assumed to be analog, but then what we are doing? We are doing sampling. Sampling makes it discrete time signal. So you had xt, you are making it to some xn, where n is a is an integer. So you are changing the index, it becomes a discrete time signal. And then if you apply quantization on this, have you done digital electronics already? Yeah, so you know this flow, sampling and quantization. So what you will get? You will get basically a digital signal, a discrete signal. So after quantization, you are getting a finite number of possible values of the signal at every discrete time interval. So this signal, which I am writing as say x hat n, and now this x hat can be of some finite values. So these finite values then we can encode using binary encoding, and if there are some n number of finite values, there can be log n number of bits by which you can represent every value. So here, for example, there are e by epsilon to the power wt number of signals, which you can represent using wt log e by epsilon number of bits. So you get a bit representation. So we completely, this is the entire flow diagram of analog to digital conversion, or A to D, and digital conversion. Now of course this rationale which I am stating right now, this was not the only rationale behind going to digital from analog. another big rationale is of course the devices, because we know that analog devices, be it a multiplier or a modulator or whatever, or oscillator or amplifier or filter, analog devices are expensive. You cannot, like even when it started 1940s or something, it used to be expensive. But in the other side, the so-called digital electronics and like integrated circuits, that grew. So the so-called VLSI domain grew. So silicon came into the silicon revolution happened. And so what started happening, like we got some really handy transistors, so those MOSFETs etc. came in, and they became really small, and we can pack them in a silicon core pretty easily. So starting from even 60s, 70s, 80s, 90s, so this silicon revolution happened, and those Moore's law kicks in. So we got really handy cheap digital hardware. So ADC, analog to digital conversion, is no longer a big deal, and once you make it a bit representation, you have the bits, then you can process the entire thing in the digital domain, and that becomes really cheap. So that was another motivation. There is a third motivation, of course, we will talk about that, to use the mathematics better, and that is one of our interests. Now let us complete the block diagram first. So what we did, so this was the original block diagram where you have source, channel and receiver. So now from the source, here we have put something which is the ADC converter. So this entire thing I am writing as ADC, such that I am having the binary representation or bit representation at the output of the source. So we can say that to be the digital source or something like that. So this can be our digital source, and this digital source is having these 4 blocks. So this is originally the original analog source, then sampling, I am writing the sampling like this is like the sampling, and then quantization I am drawing like this, and then encoding. So encoding, suppose I am writing like this, and finally the output which is coming out is a digital output. It is a discrete time, discrete state encoded output, and there is a channel. So the problem is changed a little bit, because when originally in analog communication we have started, it was a continuous time signal. The channel is having a particular kind of like a spectral representation, the amplitude and phase, suppose. So what you had to do, so before sending the signal to the channel, you have to do modulation, and that modulation fits the signal, it translates the signal in the frequency domain to the corresponding spectrum of the channel, the band of the channel, and then you can transmit it through that. But now this signal is no longer a continuous time signal, so directly you cannot really modulate it. So what you have to do, you have to like send it through the channel. You have to essentially convert it back to some analog signal, and then that analog signal has to be modulated to match it with the channel. So obviously, so here first from the signal you did analog to digital conversion. Now before sending it to channel, you have to again do the digital to analog conversion, and then again do the modulation. So what is the like purpose you are solving? Because this ADC, analog to digital, and then if you again do digital to analog, so this is kind of cancelling each other. Yeah, at the outset that is correct, because you have to do a digital to analog conversion and then you have to do the modulation. So suppose this is the modulation before sending it to the channel. But the key factor is these are kind of inverse of each other. This is cancelling this by this. Not everything is cancelled, like quantization cannot be cancelled, but still at least with some error you are reproducing the original signal. But the thing is, what is there in between? So here between this like you are getting some digital output here, and that digital output will go to this digital to analog conversion before sending to the modulation. But here you can do some digital processing. So there will be some digital processing which will take care of several issues of the channel, and using the so-called mathematics, which I just promised that for digital communication there is some big incentive which is coming from the theory, from the mathematics. That thing we will introduce here, and that will be done entirely in the digital domain. So this is a digital processing which will happen here. We'll talk about that later. Now after channel, when you receive it, again what you are receiving is an analog signal, continuous time signal, and that is exactly like the analog communication thing. So similar kind of spectrum, and that you are receiving. So first thing what you have to do, you have to do demodulation. Fantastic. So once you do demodulation, what you will get again some analog signal. Then you have to do some kind of again analog to digital conversion in some way, not exactly this way, but in some way. And then again there will be some digital processing, and finally this signal it can go directly to store digitally in a computer or something like that. You can store it, or you can again pass it through some digital to analog conversion and get some analog signal back. For example, telephone signal or audio signal or video signal, whatever, which you can perceive by your senses. So you can see in the digital communication flowchart, you are getting this digital to analog, analog to digital conversion a couple of number of times. So twice analog to digital, twice digital to analog. So what exactly we are gaining? We are gaining this computation, because we don't want to do the computation in analog domain, which is not that amount of trustworthy for most of the commercial applications, and analog devices are expensive, digital devices are very cheap. So that's why we want to replace this processing part from the analog to the digital domain. So in analog communication, this kind of processing, which can be a filter or whatever, that is done in the analog domain, but now we want to do that in the digital domain. So these will be essentially some algorithms which will run in some computer, and your computers are cheap. Computer means it can be embedded system, it can be some dedicated digital hardware as well. Now what are these processing? So for that we want to, basically our entire digital communication course we will be talking about these things, these processings. What kind of processing? So another motivation for digital communication came from the theory, and this theory actually started from 1940s. So let me talk about the history a little bit. So this AT&T, American Telephone and Telegraph, so American Telephone and Telegraph, AT&T, they had their mathematical research wing, which is called the Bell Lab. So in Bell Lab, the best of the graduates, physics, mathematics and electrical engineering graduates from the big schools, for example, the main place was MIT. So from MIT, the people used to go there, and they started developing different mathematical theories. There are basically two kinds of theories. One is basically how to improve the performance of the system, because some communication, practical communication systems were already at work. Analog communication was already developed, and that was used for telephony, telegraphy, television, and more of in army applications, even in radar and all. So to understand the performance and how to improve the performance, and secondly, to understand if there is some theoretical bound of the performance. So can we increase the performance indefinitely? That was another question. And if we can increase the performance, at what cost? Will that improvement in performance be cost effective? These things people were thinking about, and they did develop the mathematics for discussing these things, which are very pertinent. So in performance you can discuss the noise behavior, the behavior of the communication system in presence of noise. So in analog communication, you know the signal to noise ratio, you always try to improve the signal to noise ratio, right? So how to have a low noise amplifier, those kind of things. So the first big breakthrough came by Shannon. Of course, the sampling theorem was another pinnacle of success, but sampling theorem was known to the mathematicians like the approximation theorist, the analyst for like a century or so. But the exact proof came from a couple of people. So it was Shannon himself. It was by a different name. It was developed by Nyquist as well, Harry Nyquist. It was developed by Kotelnikov as well. It was developed by Whittaker. So these all people, they developed it independently. Even Norbert Wiener had some idea about the sampling theorem. Norbert Wiener and von Neumann, they had some idea about the sampling theorem as well. So these people, along with Shannon, they developed the sampling theorem. So that was one pinnacle. But the biggest thing which came out of the Bell Lab was information theory. So Shannon wrote a couple of papers, big papers, so which discussed information theory. So there was some theory in thermodynamics called entropy. You must be knowing if you've done some undergraduate physics course. So those concept of entropy that was brought into the analysis of signals. We'll go into detail of those information theory, and this information theory, it basically put the entirety of signal analysis and modulation and communication in a probabilistic framework, and from that probabilistic framework they tried to develop the performance criteria, etc., and the bounds, theoretical performance bounds. So we will talk about information theory, and this information theory says that what we have developed as the finite number of signals which is possible. So information theory says that how many bits are actually required to represent any signal having this kind of behavior, and if these signals are fundamentally probabilistic in nature, random in nature, then what will happen? So how we can incorporate those things into this framework, and when we assume that everything in this every signal in this entire flow diagram is random. So this is another departure for digital communication from analog communication, because in digital communication we are assuming that all signals are fundamentally stochastic or random. In analog communication, what you assumed? You assumed that the signals are deterministic, noise is random. So the noise which are kind of undesirable, you want to remove that, they are random. But now in the information theoretic framework, you want to think that every signal which is generated, be it continuous time signal or the discrete digital signal, everything is a random process. So this is a continuous time random process, this is a discrete time random process, digital random process, random vector, etc. Now this recast of the entire thing needs a deep introspection into the theory of random processes. So I need a background of probability theory, I need a considerable background of random process. That will be our in the initial phase we will be talking about those random process. That's why. Then from that random process, if we can understand these different stages, we can basically use the information theory in a better way. We can use those mathematics of information theory. So what we can do using information theory, there is something called redundancy in the signal. So if we will again draw the entire flow diagram, the signal flow diagram. So there is this discrete source. I am writing the complete this thing in one discrete or digital source. It will be better to say a digital source, and from that digital source the binary signals, the bits are coming out. There are lots of redundancy involved in that based on the probabilistic view of the signal source. So different symbols are having different kind of probabilities. Then information theoretically we can basically reduce the redundancy to the minimal level, and that method is called source encoding. And using this source encoding, you basically remove the redundancy, and you can like squeeze or compress the data stream to the minimum number of bits which is possible to obtain. So it was Shannon's idea of source encoding. Now after source encoding, before going to the channel, it has been observed that the channel will invariably introduce some noise, and that noise, if it is additive noise, then like what you were thinking here, you were thinking that since there are only finitely many number of detectable signals, so noise, what noise does, noise basically like blurs the signal location in that particular space. Suppose this is a finite dimensional space, the signal is sitting here. So if some noise is added to that from a vectorial point of view, suppose this is the signal vector, so it will be shifted, the noise signal will be added. So the new representation will be the vector addition of those two signals. This is the original signal, this is the noise signal, and you get the new signal. Now what is possible that you can like when you are trying to distinguish at the detector, when or the like when you want to detect the signal at the receiver side, what is done, it is possible that you like miscalculate the representation of the signal, and there will be some error in detection, there will be some error in reception. So this error, to remove this error, what you require is basically some redundancy. So first, using source coding encoding, you are removing the redundancy. Then there is something called a channel coding, where you like add some redundancy, but that will be a controlled redundancy, such that the bit stream generated from that will be more powerful to encounter any kind of additive noise. So we'll go through these theory pretty elaborately, and you will understand everything. After this goes to the modulation. So this digital to analog conversion and modulation. So first you put to the map, which will be digital to analog conversion, then it goes to the modulation, and after modulation you can go to the channel. Now once these entire things, so you can see these things are the digital domain signal processing, which is our power, and these are driven from the information theory. So after passing through the channel, when it is obtained, first you are taking this through the demodulator, and then you go to the detector. So this detection will basically do the inverse mapping, and it will give you the bit stream which you are expecting to send from here. Then you will pass it through the channel decoding. Finally, you will pass it through the source decoding. And then you can store in the digital domain, or you can, so I can write this to be the digital destination. Or you can further convert to analog signal for your usage. Now we can visualize this entire signal flow diagram in different ways. One way of looking at it, so in the earlier diagram, this digital processing, here the digital processings are essentially this and this. These are the digital processings, and this is basically the digital to analog conversion. This is again analog to digital conversion. Okay. Now modulation and demodulation and channel, this thing is exactly like the analog communication thing. So in entirety we can separate this out, and we can visualize this entire thing as a digital channel or binary channel. So we can digital equivalent of channel. Okay, actually not from here. We can say this to be the baseband channel, which is in the baseband, but the digital channel we can visualize this entire thing. So without the digital to analog and analog to digital conversion, this entire thing we can visualize to be a digital channel. So for different applications, we can visualize the block diagram in this way. So if we work in the digital channel model, then you can visualize this from a digital source, digital processing, like information theory, digital processing, which is source encoding and channel encoding, and then you are putting this to a digital channel. Then again some digital decoding. So I can write this digital encoding, which is source and channel encoding. This is some digital decoding. Finally, you are getting the digital destination. So you can see that now the representation destination. Now the representation of the digital communication system is entirely digital. But you have to be very careful to understand that in reality digital signal cannot communicate through any real channel. So communication through channel is definitely analog. It has to be continuous time signal, and which the signal has to be matched with the passband of the channel. This modulation and demodulation, that is equipped with the similar kind of modulation as you have done in analog communication. However, this is a kind of modeling abstraction. So when you are looking at it, you can use information theory in a better way in this encoding, decoding, etc. And we will talk about this mapping and detection when we talk about detection theory. There is something called estimation as well about the synchronization, because your time is in digital communication, the timeline is visualized in a piecewise manner. So timeline is partitioned. So every partition is basically sending one signal. We'll talk about all these things. So my plan for this semester is basically talking about all these things. First, we will convince about the digital source. We will talk about sampling, quantization, encoding. We will introduce information theory. We will talk about source encoding, source decoding, channel encoding, channel decoding. We will talk about this mapping and detection. We will talk about estimation. Estimation is there, which is implicit, not like written in the original flow diagram, but estimation is required from this signal itself. You estimate, and which is used in the detection, which is basically the timing information. Then we'll talk about modulation, demodulation also, because modulation, demodulation is basically the same as analog communication. So I will not spend much time. So we will not discuss about those like analytic function and Hilbert transform and those things, like double sideband, single sideband, those kind of things I will not discuss. So, but I will request you to quickly go through those things as well, which you have learned in analog communication, such that we can have a smooth run over the entire thing. Okay, so the first class, I don't want to, I want to say something more, because I got some feedback from you, even like last semester in network theory and the last to last semester in digital communication, that the topic, the mathematical, the like exposition of the topic is mathematically heavy. Now believe me, that is not in my hand, because the topic is mathematical. What can I do? And this digital communication is possibly the most important mathematical discovery, engineering inspired mathematical discovery of the 20th century. This is one of the like pinnacle of scientific thoughts and engineering thoughts. So mathematics is there, we cannot help it. But what I will do this time, I will motivate every mathematics with proper examples, proper real life problems, and this time even if it is online, but I will give you enough examples and enough assignments, coding assignments, such that you can get familiarized with every possible blocks. So we will do information theory pretty rigorously and with proper applications. So you will understand everything. These are good things. The bad things is like there will be lots of classes. So unless you follow every class, unless you listen to every class, I can tell you that you will not understand what is happening, because things will get too complicated, and the books which I will follow, you have seen I will use some 5-6 books. It will be impossible for you to read all the 5-6 books for understanding this subject. And also like every book is not for everybody. So as a teacher, my job is to understand from the books, and then basically mix my insight, my understanding in the topics, and present to you in such a way such that you understand in a better way. So please follow all the classes this is online, so you will not miss anything. Everything will be in that YouTube video, but please listen to those videos and ask me questions, because if you ask me questions, then it will be a proper interactive like semester, and you can ask to your juniors. Last semester I taught network theory to them and they interacted really well, so the overall experience of the semester was really good. So like please interact, that will help me, that will motivate me in teaching you better things. Ask good questions, that is another interesting things of this online semester. Regarding grades, there will be continuous evaluation, so whatever assignment, whatever problems I am giving you, try to solve them and submit to this Google Classroom in time, and it will be evaluated. I will try to evaluate it in time, but sometimes if I have some other job to do, so it can be a little delayed, but I'll try to individually reply to your queries, that I'm ensuring. Final grades will be a combination of all the assignments and 2 tests. So there will be 2 tests, one in February, one in April. So around the time of midsem and endsem. These tests, I'm not saying anything about that, but it will be of duration 2 hours, both the tests, and there will be some questions which you have to solve, and you have to write on paper, and then you have to scan, make PDF and upload. So that will be the formula, and based on that I'll do the grading. Okay, so let us start our journey and let us see how things move. I have some really exciting topics to teach, so please follow it properly such that we can have a successful completion of this semester. Okay, all the best. Oh, regarding lab, some professors were saying that complete it by simulation and all, but the problem is the fundamental thing is hardware. So in our MTech, there are some labs which are happening in the online mode. But one good thing about the MTech students is that they already have a BTech degree where they had some exposure about those hardware labs. But for you, unless you have the proper exposure of hardware labs, it will not be good to run these experiments in a simulation environment, because you will not get the favor. So I am not conducting any online laboratory. Once you come back, we will have all the labs, your analog communication lab, digital communication lab, or even the network theory lab for the second year students. We will do everything once you come back. If things don't improve, it is improving right now. Vaccine is coming, so we hope that by the end of this semester everything will be normal. But suppose things are even delayed, then what I will do, I will have the assignments and I will prepare the laboratory grade from those assignments. So be very serious about those assignments, the coding assignments especially. Okay, so I will have the experiments which are possible in a simulation environment, that I am doing. Those which are fundamentally hardware, those I am not doing. There is no point. Okay, all the best, and hopefully you have already listened to the Fourier analysis videos. Please go through them, because whatever I will do, those Fourier I am not teaching now. They are already there in those videos, but I will assume that those Fourier analysis are known, such that when I am talking about these finite number of signals and all, it is like this signal analysis. I am assuming you know Fourier analysis. When I am doing the random process, the random process model of the digital communication system, I will need the Fourier analysis over there as well. Those Wiener-Khinchin theorem and everything. So please be confident about the Fourier analysis. Regarding MATLAB, so MATLAB Octave, please be confident, because when the assignment starts, you will not get time to learn them, and I am not going to teach it. So I am expecting that everybody of you know programming and know usage of MATLAB/Octave. MATLAB is proprietary software, you may not have it, but Octave is free, open source, so you can obviously have it. Both are similar, so there should not be any problem. The assignments, when I give, you have to, so there will be 2-3 components. Something will be of you have to write on pen and paper. that you write on pen and paper. There will be some derivation which you have to do on pen and paper. Do it. There will be some coding part. So you have to write programs. You have to get the web forms. You have to get the like data, and then finally you prepare a PDF which will have some handwritten stuff, some web forms, some data, some graphs, etc. And you prepare your document well, the report well, and then you submit such that I can have everything in that one file. Okay. Google Classroom is a fantastic medium, so you can upload those things, you can ask your questions. If you have some really good questions, I can make additional video for solving those, answering those questions. If I can just write the answer, I'll write it. Okay. Okay, all the best. In the first week, I'm just like this introduction class is good enough. In the weekend, I'll prepare the first class on this band limited, time limited signaling. This is a difficult topic, so I'm like reading the papers. So from that paper, I'll prepare this material. But this is very exciting, and you have to understand this thing before going into this analog to digital conversion. And then we'll move to random process. Okay, bye.